We're back, everybody. We're going to finish off 3.1 and then kind of rush our way through 3.2 because it's not really much like the inverse function theorem, not really useful for us, mostly just useful for mathematicians, but we'll talk about it and then we'll go on to graphical interpretations. So if you remember from last time, we're talking about absolute extrema in this situation when you're on a closed interval. By the way, this is an open interval. If I were to show you this 1 to 5 with parentheses, that is an open interval. And well, what's this thing read? That is an open interval, and that right there does not apply to the extreme value theorem. We can't use the extreme value theorem unless it's a closed interval, so brackets on both sides. And so the way we do it is it has to deal with the extreme value theorem, which says that that if you're on a closed interval with a continuous function such as this, then the function will either have its absolute maximums and minimums at the endpoints of your interval or any critical value that is inside your interval. And as a reminder, critical values are where your derivative equals 0 or does not exist, and the function exists. So in order to find the absolute extrema of this function on the interval 1/2 to 3, we need to first find the derivative. So let's do that. L prime of x will be x squared minus 4x plus 6 minus 6 over x plus 1. Right? That will be our function, our derivative. Now, if we were to try and set that equal to 0, we'd end up with a little bit of a problem because we don't have a polynomial. But what we can do, so when we're trying to solve this, so we're going to set L prime of x equal to 0. We get x squared minus 4x plus 6 minus 6 over x plus 1 is equal to 0. So how do I solve this? Because it's not really a polynomial. Something I can do. We just started. No one's. Sorry. We just started. How do we solve this? If you had to solve it, if you were forced to solve it, this is a question on the exam. What would you do? Yeah. Denominator. That's a good guess. That's a very, very good guess. Let's see what happens. So multiply this by x plus 1 over x plus 1, multiply this by x plus 1 over x plus 1, and multiply this by x plus 1 over x plus 1. And what we'd end up with, so we get x cubed plus x squared minus 4x squared minus 4x plus 6x plus 6 minus 6 all divided by x plus 1 is equal to 0. That's looking better. That's looking like something that we can factor, hopefully. We'll stick with it. We'll hope that it can factor. And then from there, we'll see what we can do. So that's going to be x cubed minus 3x squared plus 2x. And then the 6's cancel, right? All divided by x plus 1 equals 0. And that factors quite nicely, doesn't it? There's a common factor of x. So we get x times x minus 1 times x minus 2, all divided by x plus 1 equals 0. We're going to set it equal to 0 or find where it doesn't exist. It will equal 0 where the numerator is equal to 0. So x equals 0, 1, and 2, and then -1 from the denominator. This, come on. Did I pencil out of life? Okay, it's out of life. Wonderful. Hopefully that'll charge in this little time period. I hope everyone has some fun Halloween plans. Stinks that it lands on a Tuesday. Sorry about that, guys. I don't make the rules. You're welcome to wear your costumes. I know Monday or Wednesday is technically November 1st, but if you do want to wear your costume in class that day, that's totally chill with me. Okay, let's see here. Do I have enough battery now? Let's see what happens now. So I just need to be very, very careful and just constantly put it in. So these were from L prime equaling 0. This was from L prime DNEing. Right? That's how we found those values. Can you go back up? Sure. So we find the critical values by setting the denominator or setting the function, the derivative equal to 0, or finding where it doesn't exist. It will equal 0 where the numerator equals 0. So 0, 1, and 2. And then it will not exist where the denominator equals 0, which would be at -1. However, looking back at the function, you can't plug in -1 into it. We can't plug in -1. And granted, you can't see the function just yet. But notice, so -1 cubed, fine. 2 times -1 squared, fine. 6 times -1, fine. But then 6 ln of -1 plus 1, that's natural log of 0, which doesn't exist. So that's out. So L of -1 does not exist. So x equals -1 is not a CV. It's rather an SCV. It's a semi-critical value because the function doesn't exist there. And that's the original function, L of -1. So we really need to be working, like looking out for those L, like when you're writing your notes and stuff, be very, very, and you're looking over it, be very clear about that's the original function that I'm talking about there. The derivative is over here. What I've written in light purple, that's the original function. So original function. And then 0, 1, and 2, all of those are places that I can plug in values. I can plug in 0 because then I get natural log of 1, which exists. I can plug in 1 and 2 into that thing as well, because I'll get natural log of 2 and natural log of 3, which also exist. Now, however, there's only 2 of those values that lie within my interval. These are in our designated interval. So those are the ones we'll test, 0 and 2. 1 and 2. 0 will not play a role. So now remember, we're trying to find absolute extrema. And the way we're doing that is we're plugging it into the original function to find the largest y value and the smallest y value. The extreme value theorem tells us that the absolute extrema will either happen at the endpoints or at the critical values within the interval. So how do we determine which one's which? We plug it into the function, and whichever one's the largest, that would be the absolute maximum, because that's the largest y value based on the extreme value theorem. Plug in all the points, we find the smallest y value, that will be our absolute minimum. So plug in the n values, L of 1/2. Well, that'll be, I need to just rewrite this function so I can see it. I'm just writing this down so that I don't have to keep jumping back and forth. Paste that right there, just at the very bottom for me to reference. So L of 1/2 would be 1/3 times 1/2 cubed minus 2 times 1/2 squared plus 6 times 1/2 minus 6 ln of 1/2 plus 1. Now, On the exam, if there's a problem on extreme value theorem, I've said this before, but I'll say it again. If there's a problem on extreme value theorem, you don't need to write that out. You can just compute it in your calculator. That is fine with me. That is 100% fine. The only reason why I'm doing it here for us in the notes is to remind us that we're plugging it into the original function. You'd be surprised how many students make the mistake of trying to plug that into the derivative. So let's plug that in. So 1/3 times 1/2 squared, cubed, sorry. Minus 2 times 1/2 squared plus 6 times 1/2, or just 3. And then minus 6 ln of 3/2. And I get roughly 0.11. I'm going to approximate. Then L of 1 is one of the critical values in it. So we get, I'm going to actually, is everyone okay with me now skipping writing all that stuff down and just plugging it in? Just so that we know right here that we're plugging it into the original function. But now I've got my, and if you have your calculator, by the way, a really nifty trick, especially if you have a nicer, like one of these types of scientific calculators, is you can press the back button after you finish the computation, and you can you have the exact same expression. All you need to do is just delete the insides of the where you plugged in the x values. So that's what I'm going to do. Plug in 1. And we get natural log of 2 on the end there. And so with ln of 1, we get roughly 0.17. L of 2 is also in our interval. So we'll plug in 2. Actually, 3. And this one I get 0.07. That should be good enough to round to. And last but not least, L of 3. Because that's our second endpoint. Thank you for bearing with me. That'll be natural log of 4 then. Is 0.68. All right. So the largest y value is 0.68. Not a very large y value, but for this function on that interval, that is the largest y value. So the ABS max is at 3, 0.68. And the absolute minimum is at 2, 0.07. Any questions on that? All good? That's how we find the extreme values of a function. We find the derivative, we find the critical values, we test the endpoints and the critical values within our interval in the original function. Whichever one gives us the largest y value is the absolute max. Whichever one gives us the absolute, like the lowest y value, that's our absolute min. And that is the extreme value theorem. Now, I did end up having enough time to create questions for this one. So these are good. I will be posting pretty soon some more stuff. But this will be fine for now. But as we go on, you'll start to see that there are less and less examples until there's none. The exercise answers, not there yet. So the mean value theorem, unit 3.2. It's probably one of the most important theorems that you'll see in mathematics. Like, what I could say is, in my grad textbooks, once we got to the derivatives section, all the proofs, every single proof in the derivatives section ended up using the mean value theorem one way or another. Whether it was like the original version of the generalized version, every single problem dealt with the mean value theorem. So super important. And for theoretical mathematics, you can use it in some fabricated practical applications that don't really exist, besides just me talking about them in this class and then bumping into you on the street and making up a problem. So not super useful, which is why we're going to kind of gloss over it. But it says, let f be a continuous function on the closed interval and be differentiable on the open interval a to b. So it doesn't need to be differentiable at the endpoints, but it does need to be differentiable on the inside. Then there exists at least one c value within the interval a comma b such that f of b minus f of a over b minus a is equal to f prime of c, or the more useful application of it for many proofs is that f of b minus f of a over f prime of c equals b minus a. Now, the reason it ends up being much more useful for proofs in this format, just by the nature of how many things we have to prove. However, the intuition comes far greater from this version here. And you don't need to memorize the mean value theorem. I'll provide it if it's needed for any questions or exams. So these are those versions. The one that I've highlighted with dark purple is more important. And it also gives far more intuition as to what's going on here. So f of b minus f of a over b minus a. Does anybody know what that is? The slope, yeah, of the function. Technically speaking, it's the secant line. It's the average rate of change, right? So if this is my curve right here, if this is my curve, f of x, what we're saying is there's at least one c value in the interval such that the slope of the tangent line is equal to the secant line. That's what it's saying. And it just so happens to be here and here. So if I were to draw two tangent lines, one right here, and then one right here, you'll see that when you draw them, now granted, my caveman drawings don't perfectly represent mathematics, but those are parallel lines. Good enough. So, and I'm gonna signify that these are parallel. If you've never seen this before, this notation means that these things are parallel. So there could be more than one c value, but there's at least one c value such that when you draw, like you can draw a tangent line that has the exact same slope as the secant line, or the line that connects the endpoints in the given interval. So that's what the mean value theorem tells us. That's at least the cool version of it. So there are, like, if you notice, it probably has the most strict conditions on a theorem that we've seen so far. It needs to be continuous on a closed interval, and it also needs to be differentiable on the open interval. That's a lot of conditions, but the reason for it is that things break as soon as you stop that. So, for example, this is a function that isn't continuous. So if you break the concept of continuity in the supposition, you could end up like a graph like this. And so if you were to do f of b minus f of a over b minus a, you would get a straight line here. And there's like, so that's f of b minus f of a over b minus a, but there's no with a slope of 0. There's no tangent line that you can draw here that has a slope of 0. And why we need differentiability is a similar situation. This line connecting the two endpoints. So that's f of b minus f of a over b minus a, and there's no value that's that slanted. All of them are either positive or very negative in comparison. So no tangent line has a slope like this. So that's why you need those conditions. You need to have it being continuous. You need to have it being differentiable on the open interval. Now, there is a very, very useful application of it. Well, not useful, but somewhat useful, which is called Rolle's theorem. Now, I'm a little rusty on the history of it. I can't remember if Rolle's theorem came first or if the mean value theorem came first, because the mean value theorem immediately implies Rolle's theorem, but I don't remember. Some textbooks have you use Rolle's theorem to prove the mean value theorem. Others do it in the reverse direction. So it all depends on what you want to start off with. So I don't know the history on that one, but if you look just a little bit later, here, where is it? I could have sworn didn't I make a problem that had it? No, okay, I guess it didn't. No worries. So we're going to do a few examples and then we'll call it good. So verify the conditions of the mean value theorem are satisfied by the function f(x) equals x cubed minus 2x plus 1 on the interval 1 to 3, and then find all c values that satisfy the conclusion. So what we need to check. So need to check. Number one, that it's continuous on 1, 3 bracket. But that's true because a polynomial. Because it's a polynomial, it's continuous everywhere. Because it's a polynomial, it's differentiable everywhere. You take its derivative, you get 3x squared minus 2. That's a function that is defined everywhere. Its derivative exists everywhere. So of course it exists on the open interval, but more importantly, since it's continuous everywhere, it's continuous on that open interval or that closed interval. And then 2, you need to check differentiable, so DIFF apostrophe BLE on 1, 3. That's the other condition that we need to check. We need continuity on the closed interval, differentiability on the open interval. And that's also true because it's a polynomial. Any questions on that? Both those things are true because it's a polynomial. Therefore, the mean value theorem does apply. Those are the two conditions that need to be satisfied for the mean value theorem. So, by MVT, by the mean value theorem, there exists a C value in 1, 3, by the way, such that f of 3 minus f of 1 divided by 3 minus 1 is equal to f prime of C. The mean value theorem states. Let's calculate both of those things and find out where we find the C value. So f of 3 minus f of 1 divided by 3 minus 1. Well, that is going to be just in the interest of time. So, well, f of 3 is 22. F of 1 is 0. So this is 22 over 2, which is 11. f prime of x is equal to 3x squared minus 2. So that means that f prime of c is 3c squared minus 2. And so now we set f of 3 minus f1 over 3 minus 1 equal to f prime of c. That means we have 3c squared minus 2 is equal to 11. And that's 3c squared is equal to 13. Which means that c squared is equal to 13 thirds. Which means that c is equal to plus or minus the square root of 13 thirds. However, one of those doesn't work. Not always the negative one, but in this case it would be. Because negative square root 13 over 3, that's not in the interval 1 to 3. Negative square root of 13 thirds, not in the interval. So the c value is only the square root of 13 thirds. That's the only one. Now, granted, there is like that is a value of c that will work. It's just not within our interval. What the mean value theorem says is there's at least one in your interval, but there could be more. And so if you were to draw this function, by the way, x cubed minus 2x plus 1, that function looks like this. So it's going to start out negative, and I don't know exactly what it's going to look like, but it should look like something like this. I think it only has one real root. But you're going to end up having, so from 1 to 3, it's going to look like this. That's that secant line, and you see that we have the one c value in our interval where it has a vertical, like a tangent line with the same slope. But there's also the one that's on the negative side, this one right here. So the c value, like we can find multiple c values. It's just what the mean value theorem tells us is that there's at least one in the interval, which, once again, not very useful in the real world. Like legitimately, I can think of 0 occasions where you would use this. I mean, I have a fabricated example in a second, but for the most part, this is mainly just used to prove concepts in mathematics that we do use all the time. So, anyways, so does the mean value theorem apply to f of x equals natural log of x on the following intervals? If not, explain the issue. If so, find all the c values. So over 0, 1, is that function continuous on the bracket 0, 1? So that's the first condition, right? Is it continuous on bracket 0, 1? Is f of x equals natural log of x continuous on that interval? No, because f of 0 doesn't exist. So that means it's not continuous on 0, 1. So MVT not satisfied for that interval. But if it was 0.1 to 1 or 0.05 to 1, then it would be. The mean value theorem would be satisfied on the interval 0.5 to 1 or 0.0001 to 1. It's just that 0 on the left-hand side that causes so many issues for us. However, on this one, just to save us some time, but like, I mean, we can still write it. Continuous Yes, it is. Because remember, functions that we know and love, there's a theorem we learned in section 1.5, is that functions are continuous on their domains. So the natural log, its domain is parentheses 0 to infinity. So if it's continuous on that whole interval, it's of course continuous on that closed interval right there. And is it differentiable? And yes, it is as well, because f prime of x is 1 over x, and that function is continuous because it exists for all those values between 1 and 7. You can plug in 1, 2, 3, 4, 5, 6, 7, 1.5, pi. You can plug in any of those values and the derivative exists. So f of 7 is equal to natural log of 7. F of 1 is equal to natural log of 1, which is, what is natural log of 1? 0. And then, so we have, and then f prime of c is 1 over c. So what we end up having is, by the MVT, by the mean value theorem, f prime of 7 minus f, or sorry, f of 7 minus f of 1 over 7 minus 1 is equal to 1 over c. Or I guess f prime of c, let's write that, f prime c. That's going to be natural log of 7 over 6 is equal to 1 over c, which tells us that c is equal to 6 over natural log of 7. And I guarantee you, if you plug that into your calculator, let's see here, 6, or natural log of 7 divided by 6, or 6 divided by natural log of 7. What am I doing? Is 3.08, roughly. So that is a number in our interval. Very, very fun. Very cool from a mathematician standpoint. Like I'm telling you, every theorem, like that entire section of notes when I was learning differentiable calculus at the graduate level, where we get really granular about all these things. Here we're just saying, here's the derivative, just accept it. Whereas in later courses, it's this is why, and it's a lot of chaos. But yes, Derek.
I just figured it out. Never mind.
Okay, you good?
Yeah.
All right. So mean value theorem. Let's go ahead and show you a quote unquote example of it. So suppose the position in feet of a ball is given by the function s of t equals t cubed minus 20t squared plus 100t. Should at some point between t equals 0 and t equals 10 seconds, the ball stopped moving. What does it mean when the ball stops moving? It would mean that the velocity is 0. Right? i.e., v of t is equal to 0. Now, is s of t continuous? Yes, it is, because it's a polynomial, just like before. Is it differentiable? Also, yes, because it's a polynomial. You take its derivative and you got everything you need. And so we can find by MVT s of 10 minus s of 0 divided by 10 minus 0 is equal to s prime of c. By the mean value theorem, since it's continuous on the closed interval 0 to 10, and since it's differentiable on the open interval because it's a polynomial, then by the mean value theorem, you can find the endpoints, plug them into the original function, take the difference, or rather find the secant line, and that will equal the derivative at c. But what is the derivative of the position function? That would be the v value. The derivative of position is velocity. And the derivative of velocity is acceleration. So S of 10 is equal to 0. S of 0 is equal to 0. So what we end up with is 0 minus 0 over 10 is equal to v prime of c. So v prime, or v of, not v prime of c, v of t is equal to s prime of t, which is 3t squared minus 40t plus 100. Actually, we don't even need to do that. I'm realizing now. So v of c, by definition, right? So this is 0. So there exists a c value between 0 and 10 such that v of c is equal to 0, which is all we needed to show. We don't need to find the c value. All it was asking is to show there's going to be some value. It didn't say find the value. It just said show. So all we need to do is show that v prime of c is equal to 0. We could find it. It wouldn't be too hard. We probably have to use this, by the looks of it, we probably have to do the quadratic formula, but we don't have to because it's not asking for those exact points. So that's an application, is that you could find out that there's at least some point where a ball shot up into the air will stop moving. Ta-da. Especially because you can totally find a function. Everyone can find a function mapping the position of a ball, right? That's a super easy thing to do. And that's what physicists do all the time, right? They just look at a ball flying into the air and like, oh, that's clearly t cubed minus 20t squared plus 100t. I'm being sarcastic, by the way. So that's how we use it in applications that are fabricated. But either way, I'm just going to omit this one. I don't find it to be useful. So, and we've got bigger fish to fry. Yes. No. That's 3.2. I'm lying. I'm fronting, as the kids say, right? Is that stunting? Is that what you say? No. That the quiz, the calendar's not correct. So yeah, it's just going to be 3.1. And so then we move on to the far more interesting stuff that is far more useful to us, which is 3.3, derivatives and their graphical interpretations. So as a kind of a recall, or like a reminder, a function is increasing if for all x1, x2 in your interval, with x1 less than x2, you have that the functions the function values are staggered. The one on the left is lower than the one on the right. So it's increasing over here and increasing here, right? Those are the two spots where it's increasing. Where it's decreasing, where if you have x1 less than x2, then you have f of x1 is greater than x2. So your y value at the left is larger than, so that you're going downhill. So, some observations. The function is increasing on the following intervals. So I'm going to highlight the curve. So it's increasing right here. And right here. So it's increasing from -1 to 0 and 2 to infinity. That's true. That's a fact. And it's decreasing on these two intervals. Ooh. From negative infinity to -1 and from 0 to 2. That's true. So observation 2 then, so that's just a fact that we know. And then what we know about derivatives is that they represent the slopes of the tangent lines to the curve at those given values. And what we notice is that when the function is increasing, like on the blue sections, the tangent lines are positive. Right? If I draw a tangent line here, positive slope. Draw a tangent line here, positive slope again. That one I'm not going to be able to draw like not perfectly. And then over here, once again, so all those spots where you are increasing your derivative, your tangent line has a positive slope, meaning that f prime is greater than 0. And when the function is decreasing, drawing a tangent line maybe right here, we see that no matter where we draw it, it's always a decreasing line. Over here, I can draw a decreasing line no matter what. No matter what happens, they're always negative sloped tangent lines. So it's negative. And then observation number 3 is that when you reach a relative max or a relative min, your tangent line has a slope of 0. That's a relative max. That's a relative min. That's a relative min. And all 3 situations, you have a horizontal tangent line, meaning that the slope of the tangent line is 0. So the question would be is, did Phil just make up this example to prove like that this only works here on this function, or is this something that's more applicable to everything? And the answer is that it's applicable to everything. There's a theorem. So for us, let f be a differentiable function. If it wasn't differentiable, we wouldn't really be able to use this. But if f prime of x is greater than 0 on the interval ab, then the function is increasing. On the interval. If it's less than 0, it's decreasing. And if the derivative equals 0, it's constant. That is a very, very useful theorem. So this allows us to find out whether or not a function is increasing or decreasing, which before, if you remember from Math 126, we kind of just avoided talking about that. We're like, don't worry about it. We could just, like, we gave you a graph every single time. We said, find out where the graph is increasing, where it's decreasing. And then you had to answer it and you all find it dandy. But now we can find out where it's increasing with calculus without ever having to pick up a calculator or a graphing calculator, which is really, really impressive to your friends and family, believe me. So you can bust that out this Thanksgiving when their family people come over, and just show them how much you've grown as a mathematician. So that is how we use it. Derivative positive, you're increasing. Derivative negative, you're decreasing. Derivative equal to 0, you're constant. So find the intervals of increase or decrease for the function. Okay, so I'm going to write down the step-by-step procedure. So in order to find out where the derivative was equal to 0, right? Where it's positive and where it's negative, right? How would I do that? So step 1 would be, I need to know, first off, I need to find the derivative, right? So step 1 is to find the derivative. I'm going to cut it in half here and put step 2 on the other side. but leave a little bit of space underneath the find the derivative, because we're going to add in a little extra section to it. But I want to show you what's going to happen. So we're going to find the derivative. So I've got this space reserved. So f prime of x would be equal to x cubed minus 5x. Okay. So if I wanted to know where it was equal to 0, that wouldn't be too hard to do, right? Just plug it into the function, you're all good. Like set the function equal to 0 and everything works out. What would I do if I did this? So don't write this down, don't write this down. But if I wanted to know where it was increasing, I would have to solve this inequality, which would give us x cubed minus 5x is strictly greater than 0, right? Does that look, you know, that's not a line, so that's not a linear function. That's a non-linear function. And that's an inequality. So that's like a non-linear inequality. Does that ring a bell? A non-linear inequality? No, that's unfortunate, because that's what this is. So if it rings a bell, we used to have to solve in Math 126 something like x squared minus 4 is greater than 0, where you had to go x plus 2, x minus 2. Don't write this down, by the way. This is not important. And so you get what I'd call the VIPs, which were x equals -2 and 2. And then you set up a sign chart. You remember this? And so you plug in the values, you get negative times a negative. So it was positive here, negative times a positive. So it was negative here, and then a positive times a positive. So it was positive here, right? Now with the sign chart, when we were solving this inequality, just this one, we would only circle the left and the right pieces. But with this problem, with what we have in front of us, trying to find increasing and decreasing, we want to know where it's positive and where it's negative, right? Because just finding where it's greater than 0 doesn't guarantee the other places are where it's decreasing. We need to find them. So really, we don't need to solve one of them. We just need to make a sign chart and interpret the sign chart. So that's what we're going to do. Yeah, because this was not useful. That's what I said. So f prime of x is equal to x cubed minus 5x. When we would solve those types of things, when we would solve x squared, once again, when we would solve this, x squared minus 4 is greater than 0. When we would solve that type of a situation, we needed to find the places where that function, that nonlinear function, equals 0. And that would be precisely, well, let's make it even more complicated. We also solve this type of a problem, right? X squared minus 4 over x is greater than 0. That was where we needed to set the numerator and the denominator equal to 0 to find the places to divide up our number line, our sign chart, right? Which would mean you're finding where that function equals 0 or it doesn't exist. How does that relate to the derivative? What did we call those places where the derivative equaled 0 or it didn't exist? The critical values. So we need to find the semi-critical and critical values. The reason, so now we need to find both, not just these critical values, but the semi-critical values, because even though a semi-critical value, for example, let's just look at one more thing before I explain why. So if this is my curve, and you're not drawing this, if that's my curve, let's call that 5. I don't care what it is. Let's call this 5. At 5, we have a semi-critical value. The derivative does not exist. Oh, wait. Not like that. Like this. Sorry. The derivative does not exist, but that is a place of importance. That's a semi-critical value. And notice that on one side of it, it's increasing, but on the other side, it's decreasing. So semi-critical values do play a role in finding intervals of increase and decrease. So what we need to do, so I'm going to bring this down just a little bit more just to make sure I have enough space. Step one is find the derivative and the SCVs and CVs. Done by setting f prime of x equal to 0 and DNE. So we find the derivative and we find the semi-critical values and the critical values. The critical values will play more of a role once we start talking about relative extrema. But the semi-critical values tell us more about intervals of increase and decrease. So for this function, setting f prime equal to 0, or DNE, which isn't really, it's never going to not exist. It's a polynomial, so it's defined everywhere, but we'll set it equal to 0. We get x times x squared minus 5 is equal to 0. And oh no, that's not a difference of squares. That's not like x squared minus 4. What are we to do? It is a difference of squares. It's just not a pretty difference of squares, because this thing does factor to x plus the square root of 5 times x minus the square root of 5. That's true for any situation, right? When you do x squared minus 4, we write it as x plus 2 times x minus 2. But really what it is it's x plus the square root of 4 times x minus the square root of 4. So that's why it's x plus 2 and x minus 2. That's the reason why it works. So that's not like, that's just for showing this purposes, but that's how you can factor x plus the square root of 5 times x minus the square root of 5. So our CVs I'll let you write that down. We'll catch up. Catch up for a second. Take a break in a moment. So I don't notice that I don't write any SCVs because there's no semi-critical values. They're all critical values because the polynomial is defined everywhere. Even though these aren't going to be pretty numbers, right? I mean, subjectively, that's my opinion. Square root of 5 is like not super important. So that's why I guess it's not a very pretty value to me, but maybe someone else thinks it's pretty. I'm getting sidetracked. But the point is, the function is defined everywhere. Polynomials are well defined everywhere. So f of 0 is going to exist, f of square root 5 is going to exist, and f of square root negative 5 is going to exist. So that's why they're just CVs and not SCVs. So x equals 0, square root 5, and negative square root 5.
That equals to 0.
That's where it equals. That's where the derivative equals 0. So, knowing that, that's the step 1. Step 2 is to create a sign chart. Now, there are many different ways that you've learned it. Some textbooks do it in a really, really roundabout way, and I disagree with it. The thing is, this is how I make my sign charts. You're welcome to do it however you see fit. If you follow a different, like if you look at a different resource and they do it a different way, that is fine too, as long as it's mathematically valid. I don't care, but I find that my method is the fastest. So what I like to draw is I draw a number line and I plot all my values. So negative square root 5, 0, and square root 5. And then I draw a vertical line down. That. Now, what I write here, by the way, I also write f prime up here and x down here to remind myself that I'm plugging in x values down below and that whatever sign I get up top, that's affecting the first derivative. Now, I know that seems like, well, duh, Phil, that's what we're working with. But later on in this section, we're going to have to also work with the second derivative. So it's important to label those charts to not get them confused. That's my feeling on it. You could probably skip it if you want to, but it doesn't hurt. It's just 3 extra pen strokes. So all we need to do is just pick some test values, which is what I'm going to do. So I'm going to pick x equals -3, x equals -1, x equals 1, and x equals 3. How did I pick my values?
That's a good question.
Yes.
Just the in-between values.
Exactly right. So we need to find a value in each interval within it, not on the end, like not at the end points or whatever, because that's where it's going to equal 0, so it's not important. But better, like, so yes, we pick a value in between each. How did I know that -3 was in that first piece?
Did you plug it in?
Yes, exactly right. Now, granted, I've done this long enough that I know. So square root 5 is a little bit more than square root 4. Square root 4 is 2, but it's a little less than square root 9, and square root of 9 is 3. So it's going to be some value between 2 and 3, closer to 2. But you can always use your handy dandy calculator, and the square root of 5 is -2, or like the negative square root of 5 is -2.23. So as long as I find a number past that to the left, I'm good. You could, like, if you really want to, you control me. You could find x equals -3 million. You write down x equals -3 million and test that value. Yes.
So are you using the calculator to say I plug in square root of 5, that's gonna give me -2.2, and I can round it up to like 3 and then use that as a value?
So no, I'm just finding out what that value is so that I make sure to plug in a number that is less than it or
Any
greater.
number that's less than that.
Yeah, any number that's less than -2.2 will suffice. -3, -7, -5 billion. If you want to, you can write a bunch of zeros. You totally do it. Because it doesn't matter. This has to do with what we call the intermediate value theorem. We didn't really go over it. This is not super useful to us at all. It's more for theoretical mathematics. But what it allows us to do is just test one point in each interval to determine the sign on the entire interval. So this is why I like my method. All I care about is the sign. I don't care about what the number is. All I care about is the sign. So all I'm going to do is just plug in those numbers, look for the sign. If I have an odd number of negatives, the result is negative. If I have an even number of negatives, the result is positive. So plug in -3, x at -3, that's going to be negative. -3 plus the square root of 5. We know that the square root of 5 is -2.2. So -3 plus 2.2, that's going to be negative. So it's 3 negatives, which is a negative. And so that I write that up here, and I write that it's going down. This will play a role later on. Yes.
You plug it into F prime or the.
I plugged it into F prime. That's another reason why I wrote the F prime there, to remind myself that I'm plugging this into F prime. That's where I'm figuring it out. I'm looking at this thing for all the signs. People watching the recording. I'm looking at this piece that I factored to determine all the signs. -3 is negative. -3 plus the square root of 5, that's negative. -3 minus the square root of 5, that's also negative. Then I'll plug in -1. X will be negative. -1 plus the square root of 5, that's going to be positive. Now, they're usually nicer numbers than this, and it's quick mental math, but you can always use your calculator to verify the sign. But you've got -1 plus 2.2, that's going to be positive 1.2. So that middle term is positive, and the last term is negative. We've got an even number of negatives, which results in a positive. So it's positive up here, which means that your curve is going to be increasing there. Plug in 1. Now x is going to be positive. X plus the square root of 5 is going to be positive, but x minus the square root of 5 is going to be negative. So only one negative, which means the result is negative, which means that we're negative and our function is going to be going down because it's going to be decreasing. And last but not least, we plug in 3. We get a positive times a positive times a positive in our derivative. That's no negatives, so it's positive, which means that it's going to be positive and therefore increasing. Any questions on any part of what I did here? I made a sign chart to determine where the derivative is positive and negative. There are many different ways to make a sign chart. This is my way. You don't have to do my way. You can do whatever you learned, but I find that this is the fastest way. And so that's what we do. Any questions on that?
No.
Step 3 is to step 3, f prime greater than 0 implies increasing, f prime less than 0 implies decreasing. So it's increasing on 2 intervals. It's increasing on negative square root 5 to 0 and square root 5 to infinity. And it's decreasing on negative infinity to negative square root 5 and from 0 to positive square root 5.
Well, that's it.
That's the answer. Oh my God, come on. There we go. Any questions on that? Like now that we finally finished it. So the places where it was positive, that middle interval to the left and then the far right interval, those are the positive pieces. And that's why I draw this line to remind myself that it's decreasing there, increasing, or positive tangent line, negative tangent line, positive tangent line. Yes, Derek. That was what I was going to mention. So some textbooks and some resources that you look up online, they will make you use brackets. Some places are wrong. Because of how it's defined, it makes no sense, in my opinion. So I'll give you an example of where you could use a bracket. If you get this function, y equals x cubed, when you find the derivative, you'll see that on one side of it, it's positive and the other side is positive. So technically speaking, this function is increasing everywhere. So you should put negative infinity to positive infinity. However, I will accept the answer negative infinity to 0, comma 0 to positive infinity. I will accept that answer because that's what the derivative tells you. The derivative does not tell you like the what happens at 0. And so I don't like using brackets because if I said that it was increasing from 1 to infinity, the definition of increasing says that for all x and y, such that x1 is less than x2, f of x1 is less than f of x2. I can't guarantee a point to the left of 1. So how do I know if it's increasing at 1? You see what I'm saying? That's my problem with it. Well, even it doesn't matter that it's Desmos or not. It's the fact is, if my function looks like this function, you could say that it is increasing from here beyond, but how do I know that it's increasing at 0? Because it isn't. Because if you pick a point to the left of 0, it's going to be above it. So that's my little soapbox rant. I will get off of it now. I will step down and say that you can use brackets. I will not mark down for it, but I prefer parentheses. Thank you for bringing that up. That's a good question. So I prefer parentheses, but you can use brackets if you wish. Just don't use brackets on infinity. That is not possible. We're not in topology. Now, the other thing I wanted to mention, and then we'll take our break, is it's very, very tempting to say, okay, well, I plugged in the first one and I noticed that it just went negative, positive, negative, positive. It looks like it always alternates. That's not always the case. And I can tell you firsthand that most of my exams, I try to make at least one problem where that's not the case. So don't just assume that you can just keep alternating. You don't need to test the values. You do need to test the values. Sometimes it goes negative, positive, positive, negative, or maybe it goes positive, 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 positive. It all depends. You never know. For example, tangent. This is an example. Tangent, if you draw a tangent, you'll notice that, oh wait, no. Yeah. It goes like this. That's the graph of tangent. And each interval, it's always increasing. So it's not like, and these are going to be the vertical lines are all the, those are going to be all the places where it has critical value or semi-critical values. And you'll see that every single time it's positive. So that is why I recommend to not just assume blindly that it's going to alternate. You will end up being upset on my exam if that ends up happening, if you assume that. Okay, let's take a break. Let's come back together at 10:15.
Thank you.
10:16. I thought I was going to give us 6 minutes. So people watching the recording, go stretch your legs, do whatever. All right, we're back. We got this function very similar to the to one we saw in section 3.1. So we have y equals x squared minus x minus 3 natural log of x. Now I wanted to note on this one because it's going to be important that the domain of this function is 0 to positive infinity. The function is only defined for values 0 to positive infinity. I did this deliberately because I want to talk to you about it. In order to find the critical values, or to find the intervals of increase and decrease, we need to find the derivative and set it equal to 0. So y prime is 2x minus 1 minus 3 over x. I did this deliberately to kind of show us that sometimes if you were to just look at the derivative and not realize that the original function has a natural log in it, you might think that the derivative is defined everywhere. But because the domain of the original function is 0 to positive infinity, our derivative is only defined for positive numbers, right? You can't have, the function looks like this. It's like something along the lines of this. And so it's only defined for values greater than 0. You can't have a tangent line over here because it doesn't exist there. So that's the reason why I wanted to mention that, because when you look at the derivative, you might think that it's defined everywhere when it's not. But regardless, we still solve it the same way. We need to set it equal to 0 and or find where it does not exist. So y prime equal to 0 slash DNE. Get 2x minus 1. I'm going to put a little bit of space because we're going to have to do something. Minus 3 over x is equal to 0 or does not exist. And as Chase suggested in the previous one, we want to find a common denominator. So we'll multiply everything by x over x. Well, the first two pieces, that is. And we get 2x squared minus x minus 3, all divided by x is equal to 0. What I can tell you definitively is on quizzes and exams, maybe not on homework assignments, but on quizzes and exams, these things should factor nicely. And what I mean by nicely is having integer coefficients. So it should be something nice. Your answers should be fractions or whole numbers. If they're not, that's probably an indication that you made an algebra error somewhere or an arithmetic error somewhere. Don't know where, but there must be someplace that happened. But this factors to 2x minus 3 times x plus 1 all over x is equal to 0. That gives us the SCVs. X equals 3 halves, negative 1, and 0. And this is the reason why I wanted to mention the note that the interval of the domain of the function is only 0 to positive infinity. So these things are out, not in our domain. So x equals 3 as CVs is x equals 3 halves only. So the only CV, the only critical value that we have is 3 halves. -1 isn't in the domain, and 0 is on the cusp of the domain, but it's not included. The function does not exist at 0. So when we make our number line, so that's going to be step 2 over here. When we make our number line, I'm going to do this. This is the way I draw my number line. I put a parenthesis here because that's where my domain stops. I don't want to draw a full number line because I don't want to get it twisted in my head that it goes on forever. It starts at 0 and goes to infinity. There's nothing to the left of 0 for this function. So we have 3 halves right here. And then we draw a vertical line down. I'm going to put y prime up here and x down here. And I'm going to test any value between 0 and 3 halves. You can choose whatever you want. You want to do pi divided by 6? You can do that. If you want to do pi divided by 3, you could do that. If you really wanted to, you could. But I would recommend, whenever possible, use 1, 0, and -1. Those are the nicest values that exist. So whenever you have the chance to use them, please use them. So I'm going to use x equals 1 and x equals 2 because 3 halves is 1.5. Feel free to use your calculator. If you don't know what 3 halves is, sometimes they're not as nice of fractions. Like 3 halves is pretty quick to know. But if it was like maybe 77 over 13, what is that number? Use a calculator to figure out what that fraction is, what the decimal expansion is. Plug in 1. So I want you to fill in the sign chart. You fill in the sign chart by plugging in the values into your derivative, 2x minus 3 times x plus 1 over x. Plugging it into this and seeing the sign. I want you to complete the sign chart so you get a chance to work with it. I'm going to slowly fill in the details. I do have it up here if you'd like to check your work. And don't worry if you're not quick at it yet. You can use your calculator, that's totally fine. I find that it might be a crutch if you rely on it too often, but that's not to say that you can't do it. I promise you, as you do this more and more, you get faster at it. It just so happens to work out. All right. So we've got our intervals of increase and decrease. We've created our sign chart. All we need to do, places where the derivative was positive is where it's increasing. So it's increasing from 3 halves to positive infinity, and it's decreasing from 0 to 3 halves. I feel like I want to take a picture of them, like, and not that way, like, otherwise it's going to be that's the whole thing. So, all right. So the derivative does tell us where it's increasing or decreasing, but it also does more than that, because if we know where it goes from increasing to decreasing, we know where its maximums are. And if we know where it goes from decreasing to increasing, we know where its minimums are. So if f prime of x, so let it be a differentiable function, and let f of c, like x equals c, be a critical value, a CV of f. If f prime changes from being positive to negative, so it goes up and then goes down, your tangent lines are positive, meaning your function's increasing, and then at c it'll be 0, and then it'll start decreasing. So then f has a relative maximum. At x equals c. or a local maximum, if you like that terminology more, a relative or a local maximum. And if it changes from negative to positive, meaning that your tangent lines have a negative slope, meaning that you're decreasing and then you start increasing, then you have a relative minimum. And if f prime of x does not change sign, like if it stays positive, if it, at both sides of the critical value, then we have f has neither a relative max nor a relative min. Nor. So it doesn't have either. There's nothing there. Okay, like case in point, we already drew it, but I'm going to draw it one more time just so you can see it. You don't need to draw this. This is just for reference. So the curve x cubed, even though you can't really see it very well, there is a critical value at 0. There's a horizontal tangent line there. But you see that on one side of it, it's increasing, and on the other side, it's also increasing. So there's nothing there. There's no relative maximum, there's no relative minimum. So it can happen that a critical value is neither a relative max or a relative min. But the first derivative test tells us a way to find them. So we're going to find the intervals of increase and decrease along with the x values for the relative extrema. We do that by first finding the derivative, finding the critical values, and they're all going to be critical values because this is a polynomial, which means it's defined everywhere, which means that any of the semi-critical values would be places where the derivative exists, or sorry, where the function exists, which would mean that it's a critical value. So we got to find the derivative, which is going to be x cubed plus x squared minus 16x minus 16. And we can split that right down the middle because that's a quadnomial. And as soon as you see that it's a quadnomial, your first thought should be factoring by grouping. And so setting the derivative equal to 0 slash dne, what I end up with, I'll factor out an x squared and I get x plus 1. And then from the second set of terms, I'll factor out a negative 16 and I'll also get an x plus 1. So I get x plus 1 that I can factor out. And then x squared minus 16 is equal to 0. That really gives me x plus 1 times x plus 4 times x minus 4 is equal to 0. Talk about this in just a moment. So, okay, so it does work now. Sadly, my little thingy that I used to make it extend doesn't work anymore. It's like I used to have a thing where you could make like, oh, well, that's unfortunate. Say what? Yes, it does. It does extend in the show. No, stop it. Okay, cool. I got it fixed. Oh, mostly fixed. Okay. So, what was I gonna say? By the way, when it comes to the exam and quiz time, you don't need to write this little thing that I've written on the left here, that f prime of x does equals 0 slash dne. I am merely writing that for your notes' sake. I'm writing that so that you, when you look back over your notes, you're like, okay, that's what I was doing. Not like looking back and I mean, like, what the hell was going on? So our CVs are x equals -1, -4, and 4. So we make a sign chart then. So -4, 1, and 4. And then we put f prime up top, x down bottom, x equals, let's say -5, x equals 0. It's perfect choice. X equals 2 and X equals 5. You can pick whatever one number you want though. If you wanted to pick X equals 3 between 1 and 4, that's your prerogative. It's all you. I want you to create the sign chart. Also fill in details. Okay. Good work. -1. I don't know why I wrote. Correction. I wrote 1 on my number line, but the answer was -1. So 0 is not the call. X equals 0 goes over here. And X equals, let's say, -1 or -2. I am so sorry about that. That was my bad. Please make sure you make that correction. So it goes -1. So I wrote 1. Yes. If you plugged it in, you got 0. That would mean that you chose an extra, like a point where it was critical value. So when you plugged in -1, you got 0, right? And that was because it was one of the values. That's why I messed up. Yes. So if that ends up happening, so this is a good point. If you end up plugging in a test value and it gives you 0 in your derivative, that means that your number line is wrong, that you accidentally forgot to include a critical value. Okay. So you should get negative, positive, negative, positive.
Wait. -2, negative.
So it'll be a negative times a positive times a negative based on the way I've oriented my my function. And so 2 negatives ends up with a positive.
Oh, -2. I just wrote that.
That might be the issue. Yeah, if you plugged in 2, you'll get positive or you'll get a negative. Yes.
So if I was to plug in -2 onto the x plus 1, x plus 4, and x minus 4, and my answer is a positive 12, could I just say it's going increasing?
Yeah, if you want to plug it in your calculator, you can just write positive there or negative, whatever it may be. So the reason why I don't do that is sometimes the derivative is quite long and trying to plug it into my calculator ends up being a little more daunting of a task than just checking the signs themselves. That being said, you can absolutely use your calculator to find the sign. Just plug in the number, like the test value, whatever number you get, look at its sign, write down the sign. So if you plug in -5, you should get -4 times -1 times -9. So -4 times -9. So you should get -36. That's a negative, so you'll write a negative there. That's another way to do the same thing. And so we write our intervals of increase. We're increasing on -4 to -1 and 4 to positive infinity. We're decreasing from -infinity to -4, comma, -1 to 4. And so then we also ask, do we have any relative maxes? And do we have any relative mins? And by the way, I will, if there's a problem on your quiz or your exam, so there won't be on this upcoming quiz because that's only covering section 3.1, but on further quizzes, I will provide a little section for you to fill this chart out. So don't need to worry about that. So relative max, this is why I like drawing that little picture up above, because then you can imagine where the increasing and decrease, like where the relative maxes and mins occur. Right here, when it goes from positive to negative, we're going to have a little hill, which means we're going to have a relative max. So there's going to be a relative max. And notice this says find the x values of any relative extrema. It doesn't say find the relative max. So all I need to list is the x values. If it was asking me for the relative extrema, the exact location, I would have to plug it into which function? The original, because we're talking about relative extrema of f, not of f prime. So if we want to know where the relative extrema, the relative maximums of f occur, we plug it into f. And so that's why I'm just going to say relative max at x equals -1. Whereas we see at 4, we've got a valley, and at -4, we've got a valley. So we have a relative min at x equals -4 and +4. And so that is the answer to this question. Any questions on that? Phil?
You're talking how do you find the relative max, you know?
So that's where it's going to change. That's what the first derivative test up here says. So if it changes from positive to negative, it's going to be a relative maximum. If it changes from negative to positive, the derivative that is, the derivative changes from negative to positive, it's going to be a relative minimum.
So like, for example, if I see that on the left side, negative and positive,
Mhm.
that's gonna be the maximum.
That's going to be a relative minimum. If you go like so, that's why I draw these little lines here to remind myself that it's a relative minimum. It makes a little valley.
So negative, positive, negative, positive, maximum.
No, negative to positive is a minimum. Positive to negative is a maximum. Okay,
So we don't have.
we do add -1. Goes from positive to negative. Okay. Let's see here. These are two very, very important examples in terms of algebraic manipulation. This is where our algebra, by the way, gets very, very tested. This is where our algebra gets tested. Things like this. So, if you remember, one of your, so Hector, one of our students, had asked, do we need, like, when do we need to simplify, right? And I had answered, if I'm just asking for the derivative, you don't need to simplify. But if there's something that you need to do with the derivative, it's best to simplify. So we saw it with finding the second derivative. It usually was beneficial to simplify the first derivative before moving onward. For finding critical values, this is where it makes sense to simplify and use algebra. So let's find the critical value, the intervals of increase and decrease, along with the location of any relative extrema. So I'm going to highlight that and say location. This means we need the coordinate point. So anyways, we'll find out G prime, we'll find the critical values and the semi-critical values, and we'll move along from there. So if we're going to find the semi-critical values and the critical values, that means that we need to find the first derivative. It's always a safe bet up until unit 4 that if you don't know what to do, take the derivative. At the end of the day, that's probably a good step. So G prime of X by the quotient rule, that's F prime, which is 1 times G, minus G prime, which is 2X times F, all over G squared, X squared squared. Let's do a little bit of simplification now. We have, so that's going to be X squared minus 2X squared minus 6X, all divided by X to the 4th. Thinking about something real quick. Sorry, just contemplating something about whether or not we should simplify and why we shouldn't. Do it. Yeah, like so, like we're going to. So here's the thing. So like let me just finish up this, and I'll show you what I'm contemplating. So this will be negative x squared minus 6x over x to the fourth, at which point you can factor out an x. In fact, a negative x. You get negative x times x plus 6 divided by x to the fourth. Now, I'm wondering whether or not we should cancel one of those factors of x. And I don't, because 0 may be an interesting point. If you ended up getting, will there ever be a situation, there's probably never going to be a situation that we need to worry about. So let's just further on and simplify.
The x to the fourth.
Well, I mean, you could, but it's going to be like that actually makes it a little bit harder to visualize. And so I'll share with you what happens. So I'm going to cancel one of these factors and get the g prime of x is equal to negative x plus 6 divided by x cubed. So setting g prime of x equal to 0 / DNE would give us x equals negative 6 and 0. So the only reason why I was curious, like, so let me, what I was contemplating there for a second. What if we had gotten negative x times x plus 6? You don't need to write this down. Don't write what I'm writing over here. So I'm going to change the color actually. Negative x times x plus 6 over x. What if that was my derivative? Because if I cancel the x's, then I would be getting rid of, like, then if I did this, then I just get negative x plus 6, which would lead me to believe that x equals negative 6 is the only critical value. But 0 would make this thing undefined. Like the original version of it, 0 would make it undefined. So that's why I was hesitant to cancel. Granted, since it didn't cancel it all the way, it ended up being like, it didn't end up being a problem for us. So that's why I'm okay with it. And I'm pretty sure every single situation that we'll encounter, that won't happen. So we don't need to worry about that too much. But just as an interesting little side note, that you don't need to worry about, but it is fun to think about. Okay, so we'll set up a sign chart. Oh, wrong color. As an aside, negative 6 is a critical value because g of negative 6 exists. This is a CV, whereas 0 is an SCV because g of 0 does not exist. You'll see why in just a moment. I deliberately made this problem this way because it's important. So negative 6 is an actual critical value. 0 is not. So let's plot negative 6 and 0. We'll make up our sign chart. Putting g prime up top and x down bottom. We'll test x equals negative 7, x equals negative 1, and x equals 1. So you can pick whatever numbers you want as long as they're in the interval. You can pick x equals negative 5 in that middle interval, and everything would work out just the same. Now, one thing I will mention is notice that there's a negative sign out front. So not only do we need to worry about plugging in the x value into both the pieces, but that negative sign is sticking around all the time. So this negative sign is sticking, let me make it red. This negative sign is sticking around in all three situations. It's a common mistake that students will forget about. It's not a mistake that they'll forget about, it's a common mistake that they will make. That negative sign is important in every single one of them. If it was positive, it wouldn't do anything. But since it's a negative sign out front, we need to worry about it. So -7, that'll be a negative over a negative, which is a negative here. So it is negative and therefore decreasing. Plug in -1, you get positive up in the numerator, negative down in the denominator because it's -1 cubed. And -1 cubed would end up being issue. So we get a positive here, which means that it's positive and increasing. And then plugging in 1, you get positive over a positive. And so the result is negative, meaning it's going to go down. We'll stop with this one and we'll pick up next time with 3.3.4.
Okay.
You have a question, Chase?
So the relative max goes like a negative positive with the relative minimum. So we have relative minimum of -6 to just -6.
So this is going to be asking us for the location. So, and this is the reason why I always want you to be noticing whether or like you should check to make sure that the value of the function exists. Because if we were just being asked to find the x values of relative extrema and not the location, you'll notice that you would say, okay, well, there's a relative minimum at -6 and there's a relative maximum at 0. Based on the sign chart, that's what it would say. But 0 is not a relative maximum or minimum because g of 0 does not exist. Does that make sense? That's why we need to be a little bit careful in identifying our CVs versus our SCVs. So 0 is not a relative maximum. So I'm gonna write that over here. G of 0, g or x equals 0 is not a relative max because g of 0 does not exist. And it can't be a relative maximum if the function doesn't exist there. Remember, we're finding the relative extrema of g, of the original function. So if g of 0 doesn't exist, it doesn't have a maximum or minimum there. Does that make sense?
Yeah, sort of.
Yeah, sort of. The more and more you do them, the more you start to see it. And by the way, well, never mind, it's not important. So it's increasing on -6 to 0. It's decreasing from -infinity to -6 and from 0 to positive infinity. A relative max, there is none. As we saw from above, 0 is not actually a point where we have a relative maximum because g of 0 does not exist. And then a relative minimum, it occurs at x equals -6, but we need to find g of -6 because we're looking for the location. So g of -6 is going to be -6 plus 3 over -6 squared. That will be -3 over 36, which is -1/12. That doesn't look like 12. So -1/12. 12th. Is it 12th or 12th? Is it 1/12 or 1/12? Never mind, that's not gonna work. What good are you? No, I'm kidding. So relative minimum at -6, 1/12, -1/12. And that is our answer. Any questions on it? Yes, Chase.
So for x equals -7.
Mhm.
-7 plus 6 is -1, and I just think that it would be positive.
So, like, yes, you're right. This will be -1. This will be -7 cubed, which will also be negative, but then there's this extra negative tacked on the front. So the numerator will be positive, but the denominator will be negative. There's 3 negatives total, which means the answer is going to be negative. Is that answering your question, or like, do we need to clarify more? 1 second. That's the trickiness. There's a reason why I carefully crafted this example to have that awkward situation. So that negative sign out front needs to be accounted for. Yeah. Now, granted, you could also, once again, we can always just plug in the number into the expression and call it good and see what sign you get at the end. I guarantee you, if you decide to just plug in -7, the answer you'll get is -1 343rd. It's a negative. But that's one thing. So we'll pick up next time on Wednesday with section or example 3.3.4. Your quiz on Wednesday covers only 3.1. Only 3.1. So absolute extreme of the extreme value theorem. Nothing on 3.2. I'll send an email tomorrow reminding you of that fact. And I'll also be updating the Canvas homepage with that very soon. All right, guys, if you have any questions, feel free to email me or come to my office hours. Otherwise, I will see you guys on Wednesday. Have a great rest of your day. Happy Halloween. I won't be able to see you until after Halloween, so have a great one. Make good decisions. Right? Don't do anything stupid. Don't ruin any pumpkins, anything like that. Just enjoy the ambiance of Halloween. All right, guys.